Yeah, welcome back to this lecture series. In this lecture, we are going to see the multivariable calculus. In particular, we are going to see what is a partial derivative, total derivative of multivariable functions, and then Taylor series expansion of two variable functions, and maxima and minima of several variables, and constrained maxima minima of the constrained variables, then the Jacobian of the multivariables. These are the things which we are going to see now. Now let us see the first definition of the partial derivatives. Suppose if f equal to f of x comma y, it is a function of two variables x and y. Here x and y are two independent variables and f is a dependent function. That is f dependent on two independent variable x and y. And it is a real valued function. That means if you fix the value of x and y, then the value of f is going to be the real number. That's why we call this as real valued function. Okay, real valued function. Now the partial derivative of the function f with respect to x is defined as limit h tends to 0 f of x plus h comma y minus f of x comma y upon h. If this limit exists, then we call this as dou f by dou x, and it is denoted as dou f by dou x, or sometimes we used to denote this as f suffix x. Okay, f suffix x equal to dou f by dou x. Similarly, the partial derivative of f with respect to y, which is defined as limit k tends to 0 f of x comma y plus k minus f of x comma y divided by k. If this limit exists, then which we denote it as dou f by dou y, or sometimes we used to write like this, f suffix y, right? Now let us see the geometrical meaning of the partial derivative. Suppose f is a function of x and y. Here f is a function of x and y. There are two independent variables. Therefore, the graph of f is a subset of R3. That means f equal to f of x comma y, which represents a surface. For example, see, this is our x-axis and this is our y-axis. If you plug the value of x and y, then it generate one surface like this. Okay, it generate one surface like this, right? Now, what is the meaning of dou f by dou x at the point a comma b? We have the point a comma b here. So dou f by dou x at the point a comma b is a tangent of the angle at the point. Okay, at the point a comma, this point is a comma b comma f of a comma b. Okay, so tangent of the angle at the point a comma b comma f with the curve of intersection. That means we have to draw a plane, we have to fix a plane which is passing through y equal to b. So therefore, if we pass the plane, then the plane will intersect the surface. It will generate a curve like this. Okay, it will generate a curve like this. Then dou f by dou x, which means it is a tangent which makes an angle theta with this curve of intersection of the plane y equal to b and f of x comma y. Okay, that is your dou f by dou x. Similarly, dou f by dou y means the curve, the angle of the tangent angle at the point a comma b of a comma b comma f with the curve of intersection of the surface f and x equal to a. That means we have to draw a plane which is passing through x equal to a. Then this will intersect the surface. Then this will generate a curve like this, and then it makes angle, right? This gives the dou f by dou y, right? That is the geometrical meaning of this. Okay, there are some results which you are going to use very frequently. They are nothing but addition rule, product rule, division rule, and a chain rule. Okay, the first one is called addition rule, and then this is a product rule, and this is a division rule, and this is chain rule. Okay, right? I just denoted as AR, PR, DR, and CHR, right? The first result, if u, v, w are the functions of x, y, z, and if we define the new function g, which is equal to sum of all these functions, then the partial derivative of g with respect to x, which is equal to sum of their partial derivative with respect to x, that is dou u by dou x plus dou v by dou x plus dou w by dou x and so on, if this sum which is equal to dou g by dou x. Similarly, dou g by dou y which is equal to dou u by dou y plus dou v by dou y plus dou w by dou y plus and so on. Okay. Similarly, we can define what is dou g by dou z and for any variable z. Let us see the second result. If u, v are functions of x and y, and if we define g which is equal to product of u and v, that is uv, then dou by dou x of uv which is equal to u into dou v by dou x plus v into dou u by dou x. This is called the product rule. And the division rule is, if g which is equal to u by v, then dou by dou x of u by v which is equal to v dou u by dou x minus u into dou v by dou x divided by v square. And if g is a function of u and u is a function of the dependent variable x, y, z, then dou g by dou x, first we have to differentiate g with respect to u. Why? Because g is a function of u explicitly, therefore dou g by dou u, but u is a function of x, therefore dou u by dou x. Similarly, we can find the derivative of g with respect to y, z and so on, right? This is called a chain rule. So next definition, the total derivative. If f is a function of x and y and it is a differentiable function, then the first order and the second order total derivative of f are defined as follows. That is df equal to dou f by dou x into dx, where dx is a small increment in x direction, plus dou f by dou y into dy, dy is a small increment in y direction. This is called the first order total derivative. And the second order total derivative is d square f equal to dou square f by dou x square into dx square plus 2 into dou square f by dou x into dou y dx dy plus dou square f by dou y square into dy square. Okay, this is a second order total derivative. There are some notation which we are going to use frequently. Let us denote dou u by dou x means it is simply denoting it as dou u by dou x which is equal to ux. Similarly, dou u by dou y which is equal to uy. Similarly, the second derivative dou square u by dou x square is uxx, and the dou square u by dou x into dou y which is uxy, and dou square u by dou y square equal to uyy. Sometime we will be using some other notation instead of u. We will be using g or f or h, something else. Right. Let us see some example for partial derivative of the function. If u which is equal to tan inverse of x cube plus y cube upon x minus y, then find x into dou u by dou x plus y into dou u by dou y. Right. Given that u equal to tan inverse of x cube plus y cube upon x minus y, then tan u which is equal to x cube plus y cube divided by x minus y. We can just push this function to the left hand side and differentiate it with respect to x, then we get secant square u into dou u by dou x. Why? Because the derivative of tan x is d by dx of tan x which is equal to sec square x. Okay, right. See, therefore the partial derivative of tan x which is equal to secant square x, hence the partial derivative of tan u which is equal to secant square u into dou u by dou x. We are applying this definition as well as the chain rule. And then the right hand side is it is of the form u by v form, x cube plus y cube upon x minus y. So therefore apply the u by v rule. So if you apply the u by v rule, that is x minus y into 3x square minus x cube plus y cube into 1 divided by x minus y the whole square. After simplification, we are arriving 2x cube minus 3x square y minus y cube divided by x minus y the whole square. And then multiply the above expression by x, then x into secant square u dou u by dou x equal to 2x to the power 4. You just multiply it by x. See, therefore 2x to the power 4 and then 3x cube y minus x y cube whole divided by x minus y the whole square. Similarly, you differentiate tan u with respect to y, then you will get secant square u into dou u by dou y equal to x minus y into 3y square minus x cube plus y cube into minus 1 divided by x minus y the whole square. After multiplying this expression by y, we are getting y secant square u into dou u by dou y, which is equal to x cube y plus 3x y cube minus 2y power 4 divided by x minus y the whole square. Upon adding the equation 1 and 2, we are getting secant square u into x dou u by dou x plus y dou u by dou y equal to 2x to the power 4 minus 2x cube y plus 2xy cube minus 2y cube divided by x minus y the whole square, right? Then after grouping the terms, after extracting x minus y and grouping the terms, we are getting 2 into x cube plus y cube divided by x minus y, but already we have denoted x cube plus y cube divided by x minus y is tan u. See, therefore we have written it as 2 into tan u, right? Then we want the expression x into dou u by dou x plus y into dou u by dou y. Therefore, you divide this expression, above expression, by secant square u. Hence, we are getting x into dou u by dou x plus y into dou u by dou y equal to 2 tan u divided by sec square u. But what is the sec? The definition sec u, which is equal to 1 by cos u, right? By using this, we can write 2 tan u into cos square u, and tan u is tan u, which is equal to sin u by cos u. See, therefore, if you cancel one term, then we will get 2 sin u into cos u. And there is a formula, there is a one identity, sin 2a equal to 2 sin a cos a. Okay, by using this identity, we can write 2 sin u cos u, which is equal to sin 2u. Okay, see, therefore, the final expression is x into dou u by dou x plus y into dou u by dou y equal to sin 2u. Next, let us see the next example. So before that, let us see the definition of Taylor series expansion. If f is a function of the two variables x and y is a smooth function, that means a function which is infinite number of time differentiable with respect to the x and y, with respect to the variables x and y at the point a comma b. That's what the smooth function, infinite number of times differentiable. Then the Taylor series expansion about the point a comma b is f of x comma y, which is equal to f of a comma b plus 1 by 1 factorial into x minus a into dou f by dou x plus y minus b into dou f by dou y. See, dou f by dou x at the point a comma b, that is the meaning, okay? Similarly here at the point a comma b plus the second order derivative 1 by 2 factorial into x minus a the whole square into dou square f by dou x square at the point a comma b plus 2 into x minus a into y minus b into dou square f by dou x into dou y at the point a comma b plus y minus b the whole square into dou square f by dou y square at the point a comma b and so on, okay? This is what the Taylor series expansion, right? So look at this, it is a power series expansion, in the terms x minus a and y minus b. See, therefore, sometimes we can also say that it is a power series expansion in x minus a and y minus b. That's what the note. The Taylor series expansion is a power series in x minus a and y minus b. In particular, if a equal to 0 and b equal to 0, then the Taylor series is called Maclaurin series. A particular series is called Maclaurin series, and it is reduced it as f of x comma y equal to f of 0 comma 0 plus x into fx of 0 comma 0 plus y into fy of 0 comma 0 and so on. Okay, this is called Maclaurin series. Right. Let us see the next example. Expand tan inverse of y by x about the point 1 comma 1 up to the second degree terms. That means we are going to express it as a Taylor series expansion up to the second degree term. That the expansion will be having x minus a, y minus b and x minus a the whole square and x minus a into y minus b and y minus b the whole square. These are the up to the second degree term, right? Okay. Now, given that f of x comma y, which is equal to tan inverse of y by x, and then if you differentiate partially with respect to x, what is the the derivative of d by dx of tan inverse of x, which is equal to 1 by 1 plus x square, right? See, therefore, if you apply this formula, 1 by 1 plus y by x the whole square, and then by chain rule, we are getting minus y by x square, because we have to differentiate this inner argument. While differentiating this with respect to x, we are getting minus y by x square. See, therefore, fx equal to, after simplification, fx equal to minus y by x square plus y square. Similarly, fy, which is equal to 1 by 1 plus y by x the whole square into 1 by x. Then after simplification, we are getting fy equal to x divided by x square plus y square. Then the second derivatives, that is fxx, which is equal to dou by dou x of fx. But fx is what? Fx is minus y divided by x square plus y square. See, therefore, we are plugging this expression here. And then after differentiation, we are getting 2xy divided by x square plus y square whole square. Similarly, your fxy, which is equal to y square minus x square divided by x square plus y square whole square, and fyy, which is minus 2xy divided by x square plus y square whole square. Right. Now, we are going to express the given function as a Taylor series about the point 1, 1, 1. See, therefore, we have to calculate fx, fy, fxx, fxy, fyy at the point 1, 1. That means we have to replace x equal to 1 and y equal to 1 in the above all the functions fxx, fxy, okay, and fyy, fy. In all these expressions, we have to replace x equal to 1 and y equal to 1. Right. So, these are the derivatives. And then after replacing x equal to 1 and y equal to 1, f of 1, 1 is which is pi by 4, because tan inverse of 1 is pi by 4, and fx of 1, is minus 1 by 2, fy of 1, 1 is 1 by 2, fxx is 1 by 2, and fxy is 0, and fyy is minus 1 by 2. After finding all these values, you put it in the general formula. What is the general formula? This is the general formula, right? This is the general formula. Here we are replacing a equal to 1 and b equal to 1, and replace a equal to 1 and b equal to 1, and fx value, fy value, fxx value, fxy value, and fyy value. After this, we are getting the Taylor series like this: f of x comma y, which is equal to pi by 4 into pi by 4 plus 1 by 1 factorial. 1 factorial is 1 itself. See, therefore, x minus 1 into minus 1 by 2 plus y minus 1 into 1 by 2 plus 1 by 2 factorial into x minus 1 the whole square into 1 by 2, and so on. Okay, this is the required Taylor series expansion. Yes, let us see the next example. Expand e power x into log of 1 plus y in powers of x minus y. In powers of x minus y means we have to write it in the form x minus a and y minus b. Okay, x minus a, which is equal to x. See, therefore, what is the value of a? A is 0. Similarly, y minus b, which is equal to y. See, therefore, y minus 0. See, therefore, the value of b is 0 and a is 0. That means we are going to express the function as a Taylor series about the point 0, 0. That means in particular, the series is nothing but the Maclaurin series. We are going to express a given function as a Maclaurin series. So, what is f of x comma y? F of x comma y is e power x into log of 1 plus y. And if we differentiate this partially with respect to x, and we are treating log of 1 plus y as a constant, see, therefore, we are getting e power x into log of 1 plus y. And if we differentiate f partially with respect to y, we are keeping e power x as a constant, and the derivative of log x, what is the formula? D by dx of log x is 1 by x. Okay, by using this, e power x into 1 plus y, and fxx is e power x into log of 1 plus y, and fxy is e power x into 1 by 1 plus y, and fyy which is equal to e power x into minus 1 by 1 plus y the whole square. After simplification we are getting e power x divided by 1 plus y the whole square. Now we are going to express it as a Maclaurin series. Therefore, evaluate all these derivatives at the point 0, 0. So f of 0, 0 is 0 and fx of 0, 0, 0, fy equal to 1, fxx equal to 0, fxy equal to 1 and fyy equal to minus 1. Plug these values in the Maclaurin general series formula, then we will have the nice Maclaurin series, that is f of x comma y equal to 0 plus y plus xy minus y square. There is a required Maclaurin series. So similar to this, we have this example. It is simply a polynomial. It is easy to calculate. Just look at this. We have the function f of x comma y is x square y plus 3y minus 2, and we are going to express it as a Taylor series about x equal to 1 and y equal to minus 2, right? I'll skip this. The next example, a non-trivial example, sin x into sin y. It is a trigonometric function and we are going to express as a Taylor series in powers of x and y. That means again we are expressing it as the Maclaurin series. F of x comma y is sin x into sin y, and then fx is cos x sin y, fy is sin x cos y, fxx is minus sin x sin y, and fxy is cos x cos y, and fyy is minus sin x sin y. And we have to plug the values x equal to 0 and y equal to 0. That gives the values f equal to 0, fx equal to 0, fy equal to 0, fxx equal to 0, and fxy equal to 1, and fyy equal to 0. See, therefore, the Maclaurin series up to the second degree term, which is simply this is xy. Yeah. See, next we are going to have the maxima and minima of several variable function. For this, we need to review the one variable calculus. Okay. Let y equal to f of x be a differentiable function, then the extremum of the function attains if it satisfies some properties. Extremum means either maximum or minimum, right? For minimum, first we have to calculate the stationary point of the function. To find the stationary point, we have to differentiate this function, given function, one time with respect to x and then equate to 0. That is, first to calculate what is your dy by dx and then equate to 0. Okay, that gives some point that is called x0. Okay, this point is called stationary point. After differentiating one time, equate to 0 and then solve for x, that gives a stationary point. For minimum, then you go for second derivative test. If the second derivative d square y by dx square, if it is greater than or equal to 0, then the function f of x comma y, which is attaining the minimum value at the point x0. Similarly, for maximum, to find the stationary point, equate the first derivative to 0, that gives the point x0. Okay, and then you go for second derivative test, d square y by dx square. If the second derivative at the point x0 is less than or equal to 0, then the function attains maximum at the point x0. Okay, this is what the one variable calculus says. Right. The same definition which you are going to imitate for several variables, in particular for two variable function. Let z equal to f of x comma y be a differentiable function, then the function attains extremum, that means maximum and as well as minimum. As similar to the one variable case, for maximum, first we have to calculate the stationary point. To find the stationary point x0 comma y0, first we have to equate the first total derivative to 0. Okay, first total derivative df equal to 0. So what is df? Df equal to dou f by dou x into dx plus dou f by dou y into dy. Okay, this is your df. So df equal to 0 means already we know that this dx is small increment. So see, therefore dx is strictly greater than 0 and dy is strictly greater than 0. See, therefore dou f by dou x must be 0. Similarly, dou f by dou y must be 0. See, therefore df equal to 0 means fx must be 0 and fy must be 0. If we solve fx equal to 0 and fy equal to 0, that gives the point x naught comma y naught. So very simple. To find the stationary point, first calculate the partial derivative fx and fy, equate them to 0, then solve for xy, that gives the point x naught comma y naught. After finding the stationary point, you go for second order total derivative. That is the second total derivative d square f. What is d square f? D square f is dou square f divided by dou x square into dx square plus 2, what is this? 2 into dou square f divided by dou x dou y into dx dy plus here dou square f divided by dou y square into dy square. See, this is our second order total derivative. So for maximum, you go for second order total derivative. If the second order total derivative is negative definite, there it is negative. In one variable calculus it is non-positive. Here in multivariable calculus, the second order total derivative is negative definite at the stationary point. If the second order total derivative which is negative definite at the stationary point, then the function attains the maximum. Okay. So the second order total derivative which gives one matrix, that is called a Hessian matrix, which we will see it little later. So second order total derivative which is negative definite, which is equivalent to saying that Hessian matrix is negative definite. Similarly, for maximum, first find out the stationary point x naught comma y naught. For this, fx equal to 0 and fy equal to 0, solve for x and y, that gives a point x naught comma y naught. Then go to the second order total derivative, that is d square f. If d square f which is positive definite at the point x naught comma y naught, then the function attains the minimum value. Or in other words, if the Hessian matrix which is positive definite, then the function attains the minimum value at the point x naught comma y naught, right? Okay. So what is your total derivative? Second total derivative d square f equal to fxx into dx square plus 2 into fxy into dx dy plus fyy into dy square. See, it is similar to the quadratic form. Already we have seen the quadratic form. It is similar to the quadratic form. See, therefore d square f can be written in this form, dx dy and fxx, fxy, fxy and fyy, and then the column, increment column. This is called increment column. So this matrix is called Hessian matrix. Okay. See, the Hessian matrix which is denoted as H. Okay, right. So for simplicity, we will be writing the notation R equal to fxx and S equal to fxy and T equal to fyy. So positive definite means, suppose if you have the matrix A11, A12, A21, A22, see, this is your A. Okay. If I want to say the matrix A is positive definite, then D1 is greater than 0. What is D1? D1 equal to A11. Then what is D2? D2 is A11, A22 minus A21 and A12, right? That is D2 is greater than 0. So similarly, here if H is positive definite, that is R is greater than 0 and RT minus S square is greater than 0. See, negative definite means if H is negative definite, that is R is less than 0 and RT minus S square is greater than 0, right? Okay, let me rewrite it again. For maximum, first calculate the stationary point from the first order total derivative. Then at the stationary point, if R is less than 0 and RT minus S square is greater than 0, then the function attains the maximum. For minimum, first calculate the stationary point from the first order total derivative and then calculate r. If r is greater than 0 and rt minus s square is greater than 0 at the point x naught comma y naught, then the function attains the minimum value. Okay, right. So just we are rewriting it as like this. If f is a function of x and y and fx equal to p, fy equal to q, and fxx is r, fxy is s, fyy is t. For maximum, fx equal to 0, fy equal to 0, that gives a stationary point. What is a stationary point? Here x naught comma y naught. Right. And then calculate rt minus s square if it is greater than 0 and r is less than 0. See, therefore it attains the maximum. For minimum, from fx and fy, you calculate the stationary point x naught comma y naught, and rt minus s square is greater than 0, r greater than 0, then it gives the minimum at the stationary point. Right. We will see some example by using the above definitions. Right. First, let us see the problem. Examine f of x comma y, which is equal to x cube plus y cube minus 12x minus 3y plus 20 for its extremum values. What is the meaning of extremum values? Extremum means either maximum or minimum. Either maximum or minimum, right? So given that f of x comma y, which is equal to x cube plus y cube minus 12x minus 3y plus 20, then what is your fx? Differentiate this partially with respect to x. Therefore, the derivative of x cube, which is going to be 3x square, and then if you differentiate this y cube, that is going to be 0, minus 12 into partial derivative of this with respect to x, which is going to be minus 12, and there is no x here, so therefore this gives 0, and there is no x here, therefore this is also 0. So fx equal to 3x square minus 12. Similarly, what is your fy? 3y square minus 3. Fxx is, what is fxx? Fxx is dou by dou x of fx, right? That is dou by dou x of, what is your fx? This is 3x square minus 12. See, therefore this gives 6x, right? Then what is your fxy? Fxy, that is dou by dou y of fx. That is dou by dou y of 3x square minus 12, but there is no y here, see, therefore this is 0, right? Similarly, fyy, which is going to be 6y. Now to find the stationary point, we have to equate the first derivative, that is dou f by dou x equal to 0 and dou f by dou y equal to 0. So fx equal to 3x square minus 12 and equated to 0, that gives a quadratic polynomial x square minus 4 equal to 0, that is x square equal to 4. See, therefore after solving this, we are getting 2 points plus minus 2. Similarly, fy equal to 0, 3y square minus 3 equal to 0, or y square minus, see, this is y square minus 1, okay, y square minus 1 equal to 0, or y square equal to 1. After solving this, we are getting y equal to plus minus 1. And then the combination of, what is the combination? Let us first take x equal to 2 and y equal to plus 1, and second one x equal to 2 and y equal to minus 1, right? And we have negative 2, x equal to negative 2, and we have two values for y. So minus 2 comma 1, and then the fourth point is minus 2 comma minus 1. See, these are the stationary points, and we have to calculate rt minus s square at all these 4 points, and we have to check whether it is the function attains the maximum at some point and the minimum at some point or not, right? Okay, so at the point 2 comma 1, the r is, what is your r? Your r is 6x, and rt minus s square is 36xy. So at the point 2 comma 1, the value of r at the point 2 comma 1 is 6 into 2, so therefore 12, which is greater than 0, and rt minus s square, which is 36 into 2 into 2, that is 72, again it is greater than 0, right? See, therefore r greater than 0 and rt minus s square is greater than 0, see, therefore it satisfies, or in other words, the Hessian matrix is positively definite, hence the function attains the minimum value at the point 2 comma 1. This is called a local minimum. Why? Because we are using the first derivative test. See, therefore, this is local minimum. Right. Now, let us take the second point, 2 comma minus 1, and then at the point 2 comma minus 1, r is greater than 0 and rt minus s square is less than 0. See, therefore, for positive definite, r greater than 0 and rt minus s square is greater than 0. See, therefore, we are having the another case. See, therefore, no conclusion. Similarly, at the point minus 2 comma 1, r is less than 0 and rt minus s square is less than 0. See, therefore, for negative definite, r is less than 0, but rt minus s square, that should be greater than 0. But we are having the other case, hence no conclusion at this point minus 2 comma 1. Then at the point minus 2 comma minus 1, the value of r is less than 0 and rt minus s square is 72, which is greater than 0, right. See, therefore, at the point minus 1 comma minus 2, the Hessian matrix is negative definite, hence the function attains local maximum at the point minus 2 comma minus 1. Clear? Is it clear? Right. Let us see the next example, which is similar to this. Find the extremum values of the function f of x comma y, that is x cube plus y cube minus 3x minus 12y plus 20 for its extremum values. So, given that f is like this and fx equal to this, fy equal to this and fxx equal to this, fxy equal to this, fyy equal to this. Now, to find the stationary points, we have to equate the first derivative fx equal to 0, fx equal to 0 and fy equal to 0. That gives a stationary point. Let us see those things in the next slide. To find the stationary point, fx equal to 0 and fy equal to 0. Fx equal to 0 means here 3x square minus 3 equal to 0. See, therefore, x square minus 1 equal to 0 or x square equal to 1 or x equal to plus minus 1. Similarly, here fy equal to 0, that is 3y square minus 12 equal to 0. After solving this, we are getting y equal to plus minus 2. Then the combination of the above points are 1 comma 2, then second one is 1 comma minus 2, then minus 1 comma 2, right. Then the fourth point is minus 1 comma minus 2. These are the 4 stationary points. And we have to calculate r, rt minus s square at these 4 points. See, sometimes the stationary points are so called critical points, right. Now, at the point 1 comma 2, the value of r is 6 and rt minus s square is greater than 0. See, therefore, the Hessian matrix is positive definite, hence the function attains the local minimum at the point 1 comma 2. Similarly, at the point 1 comma minus 2, r greater than 0, but rt minus s square is less than 0. See, therefore, no conclusion. And at the point minus 1 comma 2, r is less than 0, but rt minus s square is again less than 0. See, therefore, no conclusion. At the point minus 1 comma minus 2, r is less than 0 and rt minus s square is greater than 0. See, therefore, the Hessian matrix is negative definite, hence the function attains the local maximum at the point minus 1 comma 2. See, let us see the next example, which is similar to the above problem. Here it is a quadratic polynomial in x and y, x square plus y square plus 6x plus 12. It is a very easy problem, just to go through it. Now, to find the stationary points, equate the first derivative to 0. So, fx equal to 0 and fy equal to 0. Fx equal to 0, which gives x equal to minus 3. Fy equal to 0, which gives y equal to 0. See, therefore, there is only one stationary point. At the stationary point, rt minus s square is 2 and r equal to 2. See, therefore, the Hessian matrix is what? Positive definite. Hence, the function attains local minimum at minus 3 comma 0. Yeah. So far, we have seen few problems. In this, we didn't fix any constraint or condition on the variables. We have taken x, y which are running from minus infinity to plus infinity, right? There is no restriction on the variables x and y. Okay, but sometimes we will be having some constraint among the variables x, y, z. See, that is why we call this as the problem is a constraint problem. And if you are looking for maxima, minima having some constraint among the variables x, y, z, then the corresponding problem is called constrained maxima, minima problems, right? For this type of problem, first they will give the function f of x comma y to be the maximized or minimized subject to the variables x, y, z having some relation pi of x comma y comma z, like this. Okay, right. So after identifying what is your f and pi, we have to redefine a new auxiliary function capital F in this form, that is f equal to small f plus lambda into pi, where lambda is a Lagrange's multiplier. Of course, it is going to be a function of x comma y comma z, right? Now to find the extremum values, as like the previous case, we have to differentiate partially with respect to the variables. Of course, here capital F is a function of x comma y comma z, and then one more variable lambda. See, therefore, we have to differentiate capital F partially with respect to x, y, z and lambda, and then equate them to 0 and solve for x, y, z and lambda. So dou f by dou x equal to 0, dou f by dou y equal to 0, dou f by dou z equal to 0, and dou f by dou lambda equal to 0, right? That gives the nice function fx plus lambda pi x equal to 0. See, therefore, from this we are getting fx by pi x equal to minus lambda. Similarly, from dou f by dou y equal to 0, we are getting the expression fy divided by pi y equal to minus lambda. From dou f by dou z equal to 0, we are getting fx upon pi z, which is equal to minus lambda. And dou f by dou lambda equal to 0, we are getting pi of x comma y comma z, which is equal to 0. Okay, from these four equations, we have to find out the value of x, y, z and then lambda if required. Let us see the first example. A rectangular box open at the top is to have the maximum of 32 cubic centimeter, and then find the dimensions of the box which requires at least amount of material for its construction. Okay, so rectangular box, it is something like a geometry box which is open at the top, or it is similar to the fish tank. Okay, right. So it will be like this. Once again, so this is your y axis and this is your x axis and z axis, right? So this is having x units and this is y units, and then the top, height is z units. Okay, for area which is xy. Okay, for example, for a bottom plane, the area of the rectangle is xy. Similarly, the volume of the cuboid or the rectangular box like this, the volume is xyz, right? Now let us denote xyz be the length, breadth and height of the box, and then given that the condition, what is the condition? The volume is 32 cc. See, therefore, the volume xyz which is equal to 32, and then we are assuming that x greater than 0, y greater than 0 and z greater than 0. What is the condition? The condition is x, y, z should satisfy, that is x into y into z, which is equal to 32. That is the condition. Now what is the surface area? How many surfaces are there? There are 5 planes, right? First xy plane, that is a bottom plane, and then xz plane, this is your xz plane. Then opposite to that there is one xz plane, right? And then yz plane, this is your yz plane. Then for opposite to this, we have another yz plane. See, therefore, the total surface area is sum of all these area of the plates. So for a bottom plate, we have the area xy, and then there are two vertical xz planes, see, therefore 2xz, and there are two vertical yz planes, see, therefore 2yz. See, therefore, the total surface area is xy plus 2xz plus 2yz, right? But at the top, which is open, okay, open, otherwise we would have 2 into xy, 2 into xy, but at the top we are having open, hence the total surface area is xy plus 2xz plus 2yz. Now what is the constraint? The constraint is xyz is equal to 32. See, therefore, you rewrite this as pi of x comma y comma z, which is equal to xyz minus 32. So as I said, we have to redefine the new function as an auxiliary function, that is capital F equal to s plus lambda pi. What is s? S equal to, here capital S is similar to your small f in the definition, right? So s is xy plus 2 into xz plus yz plus lambda into xyz minus 32, right? See, this is your auxiliary function. Now to find the extremum value, we have to differentiate capital F partially with respect to x, y, z and lambda, and then equate them to 0. From this we have to calculate what is your x, y, z and lambda, right? So fx is y plus 2z plus lambda into yz, and fx equal to 0, which gives y plus 2z equal to minus lambda yz, and multiply it by x, which gives xy plus 2xz, which is equal to minus lambda xyz. Let me call this as equation number 2. Similarly, if we differentiate partially with respect to y, we are getting x plus 2z plus lambda xz, and equate fy equal to 0, which gives xy plus 2yz equal to minus lambda xyz, that is your equation 3. And fz 2x plus 2y plus lambda xy, and fz equal to 0, and multiply it by z, that gives 2xz plus 2yz equal to minus lambda xy z, right? Look at the equation 2, 3, 4, the right hand side are same, right? The right hand side are same, so therefore equate the left hand side, that gives one relation. Similarly, by using the value of the relations, we can calculate the value of x, y, z and lambda. So from the equations 2 and 3, we are having the relation. See, we are equating the equation 2 and 3 because the right hand side is same. See, therefore equate the left hand side. We have this xy, we can cancel this xy. If we equate these two, xy plus 2xz, which is equal to xy plus 2yz, we can cancel this term, and then after this we are having 2xz, which is equal to 2yz. We can cancel this 2 and z, so that we are having x equal to y. See, that's why we have written here x equal to y. Similarly, if we equate the equation 3 and 4, we are having the relation, or we are getting the relation y is equal to 2z. Okay, right. So the constraint equation says that dou f by dou lambda equal to 0 says that x, y, z, which is equal to 32. Okay, see, therefore xy equal to 32, and then replace x equal to y or y equal to x, and then z equal to y by 2 or x by 2. Hence we are having x cube, which is equal to 64. So after solving this, we are getting x equal to 4 and y equal to 4 and z equal to 2. Okay, this is the required dimensions. See, let us see the next example. Find the volume of the largest rectangular parallelepiped that can be inscribed inside the ellipsoid, x square by a square plus y square by b square plus z square by c square equal to 1. Okay, what it says, we have the ellipsoid like this. It is a three-dimensional object. This is x-axis and this is y-axis and z-axis. Right. Inside this, we are going to find out a largest rectangular parallelepiped which is sitting inside this ellipsoid. Okay. So what is the volume? The volume is, see, this is it is the center of the ellipsoid. Okay. See, therefore in x direction this is x unit, and then here this is again x unit. In y direction this is y unit, and z direction z. See, therefore the volume is 2x into 2y into 2z. Hence v, which is equal to 8xyz. Now the constraint is x square upon a square plus y square by b square plus z square by c square minus 1. Why? Because the variables x, y, z satisfying the condition this. Now we define the new auxiliary function capital F equal to v plus lambda pi, where v is 8xyz and pi is this. To find the stationary point, we have to differentiate capital F partially with respect to x, y, z and lambda, and then solve for x, y, z, lambda, right. So fx equal to 0. What is fx? Fx is 8yz plus lambda into 2x divided by a square, and then if you equate to 0, 4yz equal to minus lambda x divided by a square. Okay, then multiply it by x, because we want x square by a square. Because there is a constraint x square by a square plus y square by b square plus z square by c square equal to 1. We can make use of this constraint. For this, we do some algebraic manipulation, that is multiply the above expression by x, so that we will get x square by a square, right. See, therefore 4xyz equal to minus lambda into x square by a square. Similarly, see, or you can write x square by a square equal is minus 4xy divided by lambda, and then similarly fy equal to 0 and fz equal to 0, that gives minus 4xy divided by lambda, which is equal to y square by b square. Similarly, minus 4xyz divided by lambda equal to z square by c square. Okay, here z is missing, right. So what it says, the left hand side is same, right, minus so minus 4xyz divided by lambda equal to x square by a square. Here also this, therefore the right hand side is same. So that is x square by a square equal to y square by b square equal to z square by c square, right. These are all equal. So we have the constraint x square by a square plus y square by b square plus z square by c square equal to 1. See, therefore we can replace y square by b square equal to x square by a square. Similarly, z square by c square equal to x square by a square. Hence we are getting 3x square by a square equal to 1, or x square equal to a square by 3, or x equal to plus minus a by root 3. Similarly, we are getting y equal to plus minus b by root 3, z equal to plus minus c by root 3. To find the maximum volume, you take the positive value. Why? Because we are looking for the maximum volume. Hence, x equal to a by root 3 and y equal to b by root 3 and z equal to c by root 3. Hence, the volume is 8xyz, or 8abc upon 3 root 3. I hope it is clear. Then let us see the next example, which is similar to the above problem. Of course, it is easy. Just to go through it, I'll skip this. See, next, let us see the next concept, that is called a Jacobian. which is very much useful in transforming some set of variables into some other set of variables. If the Jacobian is not equal to 0, then only we can retrace the transformed variable into the original variable, right? See, therefore the Jacobian is very much important in any transformation techniques, right? So let us see the definition of Jacobian. If u and v are functions of x and y having all the first order partial derivatives, then the Jacobian of u and v is defined as, and the notation is j, which is equal to dou of u comma v upon dou of x comma y. It is nothing but the determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. This is the definition of Jacobian for two variables, right? If we have two functions u, v, w, they are functions of x, y, z, and then all the three functions are having the first order partial derivatives, then the Jacobian is j, which is equal to dou of u comma v comma w divided by dou of x comma y comma z. As similar to the two variable cases, the first row of the determinant is u and their partial derivative, first order partial derivatives with respect to x, y, z. Second row is for v and the third row is for w. It's okay, right. Now let us see one or two problems based on this Jacobian. See, the Jacobian is having some properties. If u and v are functions of x and y, then the Jacobian of x and u and v with respect to x and y times Jacobian of x and y with respect to u and v, which is equal to 1. That is a product of these two, which is going to be 1. There is very useful relation. See, next one, it is a chain rule for Jacobian. If u and v are functions of p and q, and p and q are functions of x and y, then the Jacobian of u and v with respect to x and y, which is equal to Jacobian of u and v with respect to p and q into Jacobian of p and q with respect to x and y. Okay, that is called a chain rule. It is similar to the one variable formula. Then the third property is, if x is a function of x which is equal to function of u and v, and y which is equal to some other function of u and v, and if we define h which is equal to some capital H of u comma v, then double integral over the region R h of x comma y into dx dy, which is same as double integral over the another region R dash. Sometimes we may have the same region h of u comma v into the determinant Jacobian into du dv. Okay, this is another property. So what it says, if you transform from x into x comma y into u comma v, then the dx dy which is equal to Jacobian into du dv. Okay, this is a relation. Of course, we are going to use in multiple integral in many places, right. Similarly, the same definition which we will be using in probability random process technique and multivariable calculus. In some places in engineering problem they are applying, not some places, in many places they are applying the transformation like this, dx dy which is equal to Jacobian into du dv. Right. First let us see one example. If u equal to x square plus 1 and v equal to y square minus 2, then find the dou u, that is Jacobian of u and v with respect to x and y. So what is the definition? Jacobian of u and v with respect to x and y is ux, uy, vx, vy. U equal to this, see, therefore ux equal to 2x and uy equal to 0. V equal to y square minus 2, see, therefore vx equal to 0 and vy equal to 2y. See, therefore the Jacobian, what is the Jacobian? Jacobian which is equal to 2x 0 0 2y. See, therefore this is 4xy. So next another problem, if x equal to r cos theta and y equal to x equal to r cos theta, and this is not x, actually this is u. Okay, u equal to r cos theta and v equal to r sin theta, then the Jacobian of u and v with respect to r comma theta. What is the formula? dou u by dou r, dou u by dou theta, dou v by dou r, dou v by dou theta. Okay, see this is u equal to r cos theta, see therefore u r equal to cos theta, and u theta which is equal to minus r into sin theta. Similarly, here v equal to r sin theta, see therefore Vr, this is Vr equal to sin theta, and V theta which is equal to r cos theta. Right. Now you plug all these expressions in the general formula, that gives the Jacobian J which is equal to this, in fact which is equal to r cos square theta plus r sin square theta, and we know that the trigonometric identity r sin square theta plus cos square theta equal to r. See therefore the Jacobian is Jacobian which is equal to r. Okay, this is very useful result which you are going to use in many places. Okay, see with this I close the session. Thank you.